So welcome once again to a very interesting topic on sets. In the previous video, we considered the cardinality of a set and the equivalence of sets. But now we're going to look at a very important concept titled set inclusion and equality of sets. So I put it in writing: set inclusion, set inclusion, and equality of sets. So this is what we'll be looking at in this video. In the previous video, we talked about the cardinality and also equivalence. Over there in equivalence, we made use of the cardinality of a set in definition. But that method of defining equivalence is limited. You can't use that approach when it comes to the infinite sets, but we are only concerned about finite sets. For infinite sets, we use the idea of a function, and the function we use to establish the definition of equivalence is 1-1 correspondence. But I've not taught you function, so there will be no need, not proper to use function when it is not explained. Hence, I limited it to finite sets. Now, in this video, let's start with set inclusion. That is the first one we'll look at: set inclusion. Set inclusion. Now, when we say set inclusion, what is the meaning? Before I give a definition, let me illustrate to you. Look at this. If we have two sets A and B, these are two sets. Now, when is it said for A to be included in B? When? You need to know the when, the time for A to be included in B. Now, A is included in B if all elements or any element in A is found in B. If you discover that any element in A is also present in B, then you are free to say A is included in B. Other terms that can be used synonymously are A is contained in B, or you can say A is a subset of B. Either of these are accepted. So let's give a definition in writing. In writing, this is how it will look like using our set symbolisms we've established in previous videos. You can say given two sets A and B, we say A is included in B, and write this in brackets where this symbol is the inclusion relation. If for any x that is in A, x is also in B. So this is when we say the set A is included or is contained or is a subset of B. Otherwise, you cannot say A is a subset of B. So this condition should be strictly adhered to, as it is the foundation of inclusion. It must be that any x in A is also in B. It must be that, nothing more than that, nothing less, nothing more. Then we say A is a subset of B. Otherwise, A is not a subset of B. Okay, the contrary statement that C is not a subset of B is written thus: C is not a subset of D. This is how it is written. So by the time I write C is not a subset of D, I mean there is an element in C which is not present in D. There is at least one element in C that is not found in D. So this is a contrary statement that states that C is not a subset of D. Now let's give an example to buttress a point. Example: Let A be equal to 1, 2, 3, 4, for example, and B be equal to 1, 3, 2, 5, 4. Okay, now I want to ask you a question. Look at these two sets I've given to you. Is set A a subset of B? That is set A included in B? The answer is, of course, yes. Why? Because every or any element in A is also located in B. Yes, for example, 1 in A is also found in B. 2 in set A is also in B. 3 in set A is also in B. And 4 is also in B. Because of that reason, any element, I cannot use the word any element in A is also found in B. Because of that reason, I can say A is a subset of B. And I will write A is a subset of B by the use of the inclusion relation. I believe the point is clear enough. So we are done with the definition of inclusion. So we want to look at a very important aspect of inclusion called the proper subset. Proper subset. Proper subset. Right? So once again, we also consider a definition. But before I give you the definition, I need to explain to you. Let's suppose that we have two sets X and Y, for example. Let's suppose that. Now, when do we say set X is a proper? I did not say subset of Y. I'm saying now proper subset. By subset, I've already defined it to you already. This is the definition over here of subset. The word proper is added to it, so you should take note of these. They are not the same. They are different. They have different meaning. Though the meaning of one completely swallows the other, but they are different. Get? Alright. And when do we say set X is a proper subset of Y? When do we do that? When do we say that? When do we make such assertion? You can assert that set X is a proper subset of Y if there is an element in Y, but not in S. That is the first condition you should observe. There should be an element in Y that is not in S. That is the first condition. Number two condition, X should be a subset of Y. Did you get that? I go one more time again. I said for you to assert that set S is a proper subset of Y, two conditions have to be observed. The first of the conditions is that there should be an element in Y, at least one element in Y that is not in X, in set X. That is the first condition. Number two condition, this set S should be a subset of Y. And by that, I've already explained that in the first definition. So let us put into a rigorous writing and definition. S is a proper subset of Y if there exists, if number one, there exists an element P that is in Y, but P is not in S. That is one of the conditions I said. Alright. Number two, the set S must be a subset of Y. That is, S must be included in Y. So these two conditions are necessarily for a set S to be a proper subset of Y. Take note of that. The concept of a subset and proper subset are not the same. Though the concept of proper subset swallows the concept of subset, but they are not the same. That is, a proper subset is a subset, but a subset is not necessarily a proper subset. Get that? So that is what you should observe. Very, very important. Very, very important. Let me give an example of this discussion. Let's look at an example of this discussion. Example. Let's say set D be equal to 3, 4, 5 and set let me say z be equal to 4, 3, 6, 5. Okay, now observe something. Let's look what are the first condition. Let's look out for the condition. What are the conditions for proper subset? Number one, we said there should exist an element P in Y, but that element should not be in S. Okay, now in this case, now the set we are looking at is D and Z, not X and Y as in our definition. So in this case, we can see that there is an element in Z which is 6. Got it here? But 6 is not found here. So number one condition is satisfied. That is, 6 is an element of Z, but 6 is not an element of D. Is that clear? Okay. The second condition is that number 2 here is that X should be contained or included in Y. Does that happen? Yes, it happens. Look at it. 3 is an element in D, and 3 is also in Z. 4 is an element in D, 4 is also here. 5, the same thing. That means the set D is included in Z. And for that reason, we can boldly say that set D is included in Z in symbol form. So the two conditions are satisfied, and therefore D is a proper subset of Z. In some mathematical literature, the proper subset is written like this: D, very slight, not as curved as this other one you are seeing here. So this one means that D is a subset of Z, and D is also a proper subset of Z. Hope you get that. So that is it. That is it. Now we'll go to the next concept. I don't intend making this video too long, so it will be interesting. Too lengthy video bring about boringness, and I don't encourage that. Hence, I want to make it to be short as possible and interesting. So if you are confused about the lesson, I'll be glad that you reach to me. You'll be free to tell me, and I will make sure you are clear. I'll do all my possible best to make sure you are cleared. All right. So we want to look at a very important concept which is the concept of equality. Equality of set. That is the last thing we're looking at for today, because don't forget our topic, which says here it is again. Look at it over here. Set inclusion, we're done with that. And equality of set. That is the next thing we're looking at now. All right. So we'll go over to equality of sets. So let's also start with the definition. What do we mean by equality of sets? Go to look at it carefully. Now, given two sets, X and Y, S is equal. We say, sorry, put the word we here. We say S is equal to Y, and write the symbol for that statement. Write this: if for X that comes from capital X, that X is also found in Y. And if for Y that comes from set Y, that Y is also found in X. So that is one way to define it. Let me add more page to our work. Our page is exhausted already, so I'll add more page for the continuation of the work. All right. So that is for that. Now, this definition may not be clear, but we can use inclusion instead of using the membership relation to define it by a symbol, the membership relation. We can also go by inclusion. You know, to define inclusion, we need the membership relation to define inclusion. If you observe our definition so far. All right, now this is another way you can put it. You can say two sets, X and Y are equal if set S is included in Y and set Y is included in X. You see that? So that is when you say they are equal. Now this two statements, the equality statement and the inclusion statement are equivalent. That is, this statement S is equals to Y is equivalent to the statement S is included in Y and Y is included in X. Don't forget this statement is a conjunction. In logic, is a conjunction. So these two statements, 1, 2, are equivalent. You understand? So they have the same meaning, but though they appear in different way, but they have the same meaning. So they're equivalent. Now, another way of writing this equivalence is to say X equals to Y if and only if S is included in Y and Y is included in X. So you see that. So this is how to define equality. We can use the mirrorship relation to define it, and we can also use the inclusion relation. That is, please get it clear. Know what it means for two sets to be equal. Let me use the equation relation. Now here it says S should be included in Y and Y should be included in S, meaning any element found in S should be found in Y. And the same way, any element found in Y, I use the word any, there's no exception, should be found in X. Then only in that case you say the two sets are equal. Let's give an example to buttress the points we are talking about. Example. Let's alpha. You may not say, oh, tutor, you're using lowercase letter for sets. Yes, I said that is usually from the first video. So we can use a lowercase letter for sets in some cases. Let alpha be equal to 1, 2, 3. Then, okay, let me remove this from here because it's not accepted. All right. All right. And beta be equal to 3, 1, 2. Now, if you observe carefully, you see that, okay, before that, let me do something that is logical, extremely logical. 1, 2, 3, 1. Look at these two sets, alpha and beta. Are they equal? Yes, they are equal, but from the definition, what's the definition? Is that each element or any element in alpha should be found in beta. Now I said, and any element in beta, set beta, should be found in set alpha. And if you look at it and reason on it, the condition holds true because 1 is found in alpha, 1 is also in beta. 2 is in alpha, 2 is also in beta. 3 is in alpha, 3 is also in beta. The reverse is the case. 3 is in beta, 3 is in alpha. 1 is in beta, 1 is in alpha. 2 is in beta, 2 is in alpha. 1 is in beta again, 1 is in alpha. 2 is in beta, 2 is in beta. 3 is in beta, 3 is in beta, 3 is in alpha. 1 is in alpha, 1 is in beta. So you see, that is how it is done. So the repetition does not matter. So in this case, alpha and beta are equal, and we can write alpha is equal to beta, or we simply write it using the listing format of a set or the roster format of the set. So these are to define the quality. So we are done with this video. So in case you are not clear with what we've discussed so far, you'll be free to get across to me, and I will try my possible best to make it simple to your understanding. I'd like to pass across the information that we also render one-to-one service. If you're interested in a personal coaching, a personal tutoring, you can signify, and we will be glad to be your tutor, provided you have the necessary equipment, just as I'm using to instruct you now. Yet, I have an equipment I'm sharing with you, which is my laptop. But you may not necessarily need laptop. You can have other cheaper device that will enable you to connect. Then we can do a one-to-one conversation, and that is very, very important, very, very good, because then you can ask me any question. We'll meet within the live. We'll be live during the program. After the elapsed time, you can go for your break. So it's all right. Have a good day. We are done for the now. So you go have a good day. Thank you.